For the second half of this talk, I want to introduce the concept of convolutional layers and the idea of collaborative filters and some more advanced network designs. So we've, up until now, just discussed some very basic neural networks, these densely defined neural networks. And in practice or in current research, it's much more common to use more sophisticated types of layers and to organize those layers in more kind of clever ways. The motivation for what's referred to as a convolutional layer comes from the fact that dense networks, or fully connected layers, have no information or no preference in terms of spatial orientation. So if we think about those nodes, those diagrams that we had before, and we just re-index all of the values in our data set, so if we do it in one specified way, the network will still achieve the same performance. It doesn't matter if it's in order or if we've scrambled it. So long as we've done that in the same way for all of our data, it will still achieve the same performance. And that's nice in some sense, but it's completely undesirable if our data is actually highly organized. If we have an image, for example, we don't want to try to optimize a network that doesn't care what order the pixels are in. That's very valuable information. So we want to define something which is more spatially aware. And this is helpful in particular for images, but also from a more kind of mathematical standpoint for function values or anything where there is spatial correlation in your data. The basic idea behind a convolutional layer is that of filters. And these filters are designed to slide across your values and to identify specific features in certain positions. Okay, so we want to isolate local features, local patterns, and the way that we can do this is by defining an array of values, array of weights, which will be learnable parameters. So these will be the weights that we're tuning, similar to the W values in the dense setting. And what we'll do is multiply these somewhat in the fashion of a mask, element-wise. So we'll line this filter over the elements of the array, and we'll multiply the value W11 by the value directly underneath it. In particular, it's not matrix multiplication directly, even though these are typically shaped in some rectangular fashion. So we're just going to use element multiplication in terms of the filter weights. So as a kind of more concrete example of how these work, we can imagine sliding a filter in steps of 2. So this is referred to as stride. We'll get into some of the more specific details of this later, but for our purposes, we just look at this filter here that I've placed in the upper left-hand corner. So we imagine here is W11. Beneath it is the value X11, so we multiply those two values together. Similarly, W12 is shadowing X12, multiply those values together, and we sum the results in addition to a single fixed bias term. And that's passed to the activation function. Now, if we imagine sliding this over in a step size of 2, or sliding it by 2, we'll land in the upper right position. And in this position, we're still going to use the same weights. It's still W11, but now W11 is over the value X13. Okay, and so we proceed in this fashion. We apply the same weights, just multiplied by different values, and go down once we reach the end of the row and over so that we've covered, to some degree, this entire structured data as input. And those values are themselves organized in space, as we see here to the right. So we still keep those feature values in this kind of upper left, upper right, lower left, lower right format. So that we're still maintaining the spatial positioning of those features. Now, if we want to implement this, again, we want to cast everything in terms of linear operations so that we can do this efficiently numerically. And the matrix, the actual weight matrix associated with these filter weights is very kind of simple. It's very sparse, highly structured, and has very few weights. And In particular, if you go through and you expand all of those equations that I put on the previous slides, you get a matrix which looks like this. And we can kind of see the stride of 2 here, and we've vectorized our input arrays and our output arrays, and those will be basically packed back into the right shape after this is performed. And just a note, the bias and activation have been omitted just so it's a little more clear. So if we do a floating point count on this, it's a little bit more technical, but what we see is there's basically at the upper bound of this, if we adjust some parameters, it can be a little less than this. But at the upper bound, we'll have the k-squared filter weights multiplied by some of the input values in all of the r-squared positions. So if we have an r by r image, we're going to kind of take that filter in every position so that the upper left entry shadows every entry of the input. Then we'll get k-squared times r-squared multiplications. We also add those, the results, if you look back on the previous slides. So we have an addition operation here, which will correspond to k-squared minus 1 times r-squared addition operations. And then finally, we have r-squared addition ops for the biases to reach a total of 2 times k-squared r-squared flops. Okay, so the true value will be slightly less depending on your choice of what's referred to as padding and the strides, but it's generally close, and it's at least in this relative range. So similar to the convolutional layers, we can actually define what's referred to as a transposed convolutional layer, which builds up in a certain sense. It kind of is the opposite direction of a convolution. And the way that it's defined is, as the name suggests, simply by taking the transpose matrix of the original convolution matrix. Okay, so here we're going to take one value and from that produce 4 values that will populate the upper left-hand corner of this new larger set of features. And to do that, as I mentioned, we just take the transpose and we define basically just weights W11, W12, W11, W12, corresponding to the multiples of the values, the input values used to produce the output values. So we have these convolution layers, these convolution transpose layers. They're used to find local features, but in reality, we want to find many features. So it's not often that there's just one feature that we're looking for. We want to have a collection or a set of features. And the way that we can do this is by channels. So this is coming from kind of the terminology of images. We have the R, G, and B color channels. But more generally, we can think of channels as just being different stacks or collections of features that we can expand or contract as needed. So we may want many different filters, and we want to extend the notion of convolutional layers to this situation. And what we can do is quite simply connect, much as is the case in the fully connected layers, connect each layer of the input with each layer of the output. Okay, so we'll have a separate collection of these filter weights for each input channel and each output channel. So this will give us a total of n times m weight matrices. We'll use that or apply that to the input channels, sum the result for each channel, and add a bias specific to that output channel. And this, again, is implemented for us in TensorFlow already. Also, I should note, just motivating later, the second half of this talk, the weight matrices typically correspond to filters that have the same shape, just by convention. But we'll see later that you can actually generalize this, and there's ways to have filters of different shapes to capture multi-scale effects or features. And lastly, we've already done the floating point counts for a single layer. Here we see, not so surprisingly, that we just multiply that by the number of kind of layers, the m times n connections between the channels, to get the flop count for a multi-layer convolutional layer. But what's important is that, unlike the case of the fully connected or dense network, our number of trainable parameters is actually much less than the number of flops. We have k squared times m times n, and that r squared, which is typically quite large for things like images, is absent because we're using those same weights, those same learnable parameters in every position. And so this is a benefit, especially when working on something like a large resolution image over the previous dense layers. So this is a small enough number in most cases, but what's important to note is that this k is quadratic or impacts the number of trainable parameters in a quadratic fashion. So the filter size has to be kept relatively small. So if we have typically something like a 2x2 or a 3x3 filter, we can do that quickly. And there's not too many weights to adjust, not too many gradients to compute. But as that gets larger, something like a 9x9 filter is quickly becoming impractical to actually use in a network. And we'll see how to get around that later. Another aspect that may be worth noting is that these local features, if we're only using a 3x3 filter or a 2x2 filter, for instance, may only be able to detect very small local properties of the original input data. And we may expect that that's inefficient or it's not capable of getting kind of higher level features. But we can actually get around this by composing these convolutional layers in series. And what we see is that the receptive field, or the area or region of influence on entries further down in the network, grows the more layers as we increase the number of layers. So originally, this value here is impacted, in this case, by the entries in the upper left-hand corner. But if we had used a 2x2 filter to create these entries, then we see that it grows to be a much larger region on the original input data. So this is referred to as the receptive field with respect to this output value. Okay, so we can still get the larger features. We just need to compose these in series. Also, just a note on how the convolutional layers are computed. So the weight matrices, as I pointed out, are very sparse, very structured. They're organized in a very clear way, and they only have a few distinct values. So in practice, we probably won't actually form this matrix directly. And in particular, there are specialized libraries, such as the neural network library, QDNN, which have already implemented optimized versions of the primitives for deep learning methods. So things like the fundamental building blocks of carrying out a convolutional layer are implemented in this library, specifically optimized for GPUs. And so if you remember from the slides from yesterday, one of the steps for working with TensorFlow on or with GPUs is to install this library. And this specifically handles the efficiencies and optimizations that are possible due to this highly structured weight matrix that we're working with. Okay, so the convolutional layers can go quite fast, especially in the presence of hardware acceleration. And then one other technical note on in terms of the numerical computation behind this, a paper relatively recently was published demonstrating that actually we do not need to use the full precision of a float 32, for example, in order to get an accurate and precise model. We can actually train with fixed point numbers, fixed point 16-bit numbers, and by using a special rounding scheme, a stochastic rounding scheme, which basically rounds randomly based on how close you are to the next increment in the number representation, you can actually maintain that floating point 32-bit accuracy. And so I just bring this up to point out that there are many different aspects and areas of research in neural networks. It's not just the design, but also the optimization and some of these computer science or numerical kind of representation concepts as well. So early on, I mentioned something about stride. And here I just give a brief summary of what I kind of said before. It generalizes a little bit. We can have horizontal stride as well as vertical stride. This just means that we can move from the left to the right in one step size and up and down in another. And this also generalizes to 3 dimensions, 4 dimensions, etc., quite naturally. One of the more important things, or somewhat more tricky to get a handle on, is that of padding. And padding is used to determine what positions of the filter are actually admissible. So for instance, what happens when we reach the end of a row? Do we keep going until we've kind of achieved every position, or do we stop as soon as we hit the edge? And there are 2 common solutions to this. There are a few extras, but these are the 2 that are implemented in TensorFlow. One is referred to as SIAM padding, which simply incorporates zeros or adds zeros around the edge or the boundary whenever the filter is sliding off. And I'll show diagrams here in a second. And the alternative is valid padding, which only allows the filter to take positions in which all of its filter weights are above values from the original input. So no zeros will be added. So for example, if we just have a 2x2 filter on a 3x3 input, and we take a stride 1, so we're just going to move over side to side till we reach the end as determined by the padding scheme, and then move down until we reach the end again as determined by the padding scheme. With valid padding, we'll start off, we'll move over, and then we'll realize that if we kept moving over one more position, we would run off the edge. So in the valid padding scheme, that would not be admissible, so we'll return over to the next row. We'll do the same process, and once we reach this, we realize that we cannot go over to the side, nor can we go down, so we are finished, and the resulting array has a smaller size as a result or a consequence of this. So we have a 2x2 array produced because we couldn't kind of run over the edges. In SIAM padding, we'll actually get the same sized array in the end, which is the reason we refer to it as SIAM padding. And the way that we do this is we simply tolerate running off the edge, and we'll assign values of 0 to these, or just simply not include them in the calculation, to extend basically this array to the original size 3x3. So we'll do that again, and then we'll fall down off to the bottom, and then the final position will be here. We stop once the filter would be completely off the input array. So just a quick look at SIAM and valid padding. The kind of advantage of SIAM padding is that it produces something of the same size. It also always ensures that every input is included, but it adds zeros near the boundary, which can lead to maybe kind of false positives or detection of features which don't exist. So in that last entry, for instance, this is not a very accurate representation of that feature, really. It's just taking into account one of the values, and so it may say that the feature is there, but in reality it's on the edge. So it has some issues at the edge. And then valid padding has the advantage that it only uses the original input, but the disadvantage that it may not use all of the values. So in the case of adding stride, you may get to a position where there's still a few values left in the row, but you can't move over without running off the edge. And so it will not take into account those values in that situation. Some pretty visual and informative references are provided by this paper here on arXiv, as well as the associated GitHub page. And so you can see some of these kind of diagrams, and they have animations and the source code for how to make these animations, as well as some additional types of padding that are possible, but not defined by default in TensorFlow. And yeah, there is something of an arithmetic for these convolutional layers in terms of strides and padding. And for the most part, you kind of just have to work with them for a while to get a feel for how the shapes and dimensions will come out. And we'll go through some examples to see how that works. So just briefly, I want to go through the 2 kind of concepts, downsampling and upsampling, and point out some things that I've learned throughout my research, which Well, first of all, downsampling, it's very common to, instead of using the stride from that first example in a convolutional layer to decrease the size, we may want to just use a dedicated downsampling procedure such as max pooling or average pooling. So these are designed specifically to reduce the spatial resolution of our data, and that may be more natural than just doing that artificially by sliding our filter over. And it can work better for certain applications. The kind of adjoint operation to that is upsampling. And what we can think of in terms of upsampling are those transposed convolutional layers. But if you remember what those were, we were really just multiplying a single value by 4 different values to get 4 different outputs. It's a very simple idea, and it can be a little bit too naive of an operation in some sense in some applications. So again, it may be helpful to just use a dedicated upsampling procedure, and 2 that are implemented already within TensorFlow that I thought I'd point out are interpolation, such as bilinear or bicubic, and also nearest neighbor. So bilinear and bicubic will give you some smooth predictions. If you're working with something like edge detection, you may want nearest neighbor. This can have these sharp discontinuities. But these are often better in terms of performance for your upsampling if you have an application where you need to create a larger feature. And one more note is when we're working with data, we want to keep the data capacity or the size of our features relatively constant, or to increase it slowly or decrease it slowly. And as a rule of thumb, typically as we decrease our spatial resolution, so we're getting these smaller features, in order to keep the data capacity relatively constant, we want to expand the number of channels. And so this is like a typical diagram. We start out with a large spatial resolution and relatively few layers, and maybe as we have that spatial resolution, we'll double the number of features. So it will still be decreasing, but it will be decreasing linearly and not quadratically at least. And as we continue to do that, we just follow the same procedure. And typically, we do use something like a constant growth rate to determine how many channels we have. Conversely, if we're building up, if we're upsampling, we want to decrease the layers. We don't want to come from relatively few or a small set of features and create a lot of information, because there's only a fixed amount of information that we're working with. So to keep that data capacity increasingly at a manageable amount, again, we decrease the channel count as the resolution increases. And now just going back to some TensorFlow, so for the rest, I'll try to show how to implement these in TensorFlow as well, and also some of the more advanced convolutional layers. So if we want to implement convolution and pooling, instead of using convolution with stride, for instance, we can use a tf.layers module and define a network which takes, say, an input of 64 by 64 with 1 channel and creates 4 features using filters of size 3. Add a ReLU, and then after that, I can take this max pooling layer, apply to that, apply it with a stride of 2 and a filter size of 3. So it will just take the maximum under that 3 by 3 filter, and the result, since I've used a stride of 2, is to have the spatial resolution. So it'll go from 64 by 64 to 32 by 32. And we can continue to do this to get smaller and smaller resolutions, and typically we increase the channel count as we do that. Going the other way, just an example of how you would implement interpolation or transpose convolution first. It's very simple. So this will result in a increase in the spatial resolution by a factor of 2, since we've used strides of size 2. And then if we use valid padding, we'll get a slightly different solution, which is we'll double, but we'll also get 1, this kind of remainder. So this is what I was referring to, is there's something of an arithmetic to these convolutional layers. So you may want to test this out using, for example, tf.eager, enable eager mode. just to see what the size of these are. If you're using same padding, it's relatively easy. Strides of 2 for transpose convolutions correspond to increases in resolution by a factor of 2, and for standard convolution, you would decrease by a factor of 2. For valid padding, it gets a little bit more complicated. As I mentioned, transpose convolution is not always a great idea, especially if you're working with smooth data and you want to progressively build your, the resolution of your prediction. Instead, you can use bilinear interpolation. And so this is provided by TensorFlow in the tf.image module. And as you can see, we can just use a standard convolution without using any strides or using stride 1, and then apply the interpolation to produce a larger resolution. Okay, so the convolutional layers are very helpful, and they've been used to define a lot of very effective networks. But more than just using these convolutional layers to identify spatial features, it's important to actually take into consideration the layout, the organization, and how the layers interact with one another. And so the inception papers, this inception network developed at Google, introduced this idea of using filters collaboratively by defining them in these blocks, or modules, as they referred to them, which basically allow filters of different sizes to be combined and to process data in a multi-scale and multimodal fashion. So instead of just passing our values into, say, a 3x3 convolution, as is kind of the conventional or standard way, we may imagine looking at 3 different scales. Maybe just a 1x1, just looking at it pixel-wise, a 3x3, and a 5x5 convolution. So we have these multiple scales, and then we also consider this different modality of processing, max pooling, since it typically gives an improved performance when included. So we want to combine all of that information, and what we can do is combine it just by concatenating those layers. So we have a stack from the first 1x1 convolution, and stacks for the remaining 3, and we'll just combine those or concatenate those channel-wise. So this is referred to as the naive version in the original paper, in the inception paper. And the reason why it's referred to as naive is that that max pooling block is going to produce features or channels, a channel count, which is identical to the original input. So say you had 100 input channels, this will produce 100 input channels. And in order to balance the influence of each of these modules, or each of these layers rather, we would naturally choose to place 100 channels out here, here, and here to get a total of 400 channels. But as you can see, this is going to grow the number of channels quite dramatically and kind of lead to an increasing level of computational complexity, which we don't want, or at least it will be more computationally expensive. So to balance the impact without having to just replicate this channel count, we can instead use 1x1 convolutional layers to mix the channels together in this kind of linear or nonlinear fashion in the actual implementation. And so we use these as a form of dimension reduction in the channel dimension, and add these before the computationally expensive layers like convolutions and after the max pooling, so that we apply the full max pooling layer, then reduce the number of features produced by that so that we get a balanced but computationally manageable block. So this is the inception block version 1, so from the first version of the first paper. And so what these 1x1 convolutions will do is they'll basically just rescale values in the original input, and they'll add the channels or the features together before applying the convolution. So this is one improvement to the original naive version, but it's still an issue. There's still an issue regarding that 5x5 layer, as we mentioned in the slide on the computational flop count or the trainable parameter count. we have this k-squared term. So the 5 is going to, that 5 is going to be squared and have a quadratic influence on both of those properties of the model, and we want to somehow alleviate that problem or work around that in some way. And so the second embodiment of the inception block came up with the idea, or made use of the idea, that we can actually somehow factor this 5x5 or these larger convolutional filters by a series of smaller ones. Okay, so as pictured here, we can think, going from bottom to top, of a 5x5 filter or a space that we want to take into consideration. If we slide a 3x3 filter across that, we'll get a resulting 3x3 set of features here. And then using one more 3x3 feature, we get a single value, but its receptive area on this original bottom layer is 5x5. So these two 3x3s can be used to mimic, at least in the sense of receptive fields, the 5x5. Okay, and so this is only an approximate factorization, but in practice it tends to work quite well. So the idea, this improvement, we take the same kind of basic idea from before. We have a 1x1, so we're using this dimension reduction. But now, instead of applying a 5x5 filter, we'll factor that through two 3x3 filters. Okay? And it will work out to be approximately a 5x5 filter, as illustrated on the previous slide. So to implement this, I would recommend defining a custom layer, which is relatively easy to do. Just say def inception v2, for example, if we want to implement that final version. And what we basically do is define towers, these kind of compositions of layers, for each of the blocks in the diagram. So if we look at the 1x1 and 3x3 tower here, we can implement that by processing the input x by a convolutional layer with stride 1, followed by a convolutional layer applied to that hidden unit with a filter size of 3. And the 5x5 filter, which has been factored, can be implemented in the same way. We just restart using that original input x and apply 2 more additional convolutional layers. Okay, and the same for the max pooling, same for the 1x1, and at the end we just concatenate these channel-wise by indicating the third dimension. Okay, and so just one point on a technical or practical note. So if we wanted to factor these larger filters, technically that's just a linear operation. We're just trying to factor the weight matrix. So we would only apply the activation functions or the nonlinearity at the final layer of each tower. But in practice, it always turns out that, or at least in these tests, that the nonlinear, incorporating the nonlinear function at the intermediate layers provides an improved network or improved model. It increases the performance. And in part, you can think of this due to the fact that really this factorization is not, strictly speaking, possible. The number of filters connecting the bottom layer to the top layer, which are formable using 2 3x3 filters, is actually a subset of the number of features or filters that are possible with a 5x5 filter. So we add these nonlinearities, and it kind of helps make up for that in some heuristic sense. And 2 other network architectures that I just want to touch on briefly that I think are worth mentioning are ResNet, so this idea of residual learning, which works with the idea that, our network layers, as defined up until now, have always been targeting defining these full features. The h of x, say, is what the target features are. And we have to produce those from scratch. The idea behind residual learning is that it's possible that the features that you had at the previous layer were close. There's some approximation to the features that you actually wanted, and that what you should actually learn is just the difference, the residual, kind of the delta, so to speak, between your current features and the target features. So you kind of just want to learn this incremental value rather than the full set of features. And this can be implemented into neural networks by adding what are referred to as shortcuts or skip connections. And these allowed the inputs to pass through unchanged, and then we can use that unchanged value to basically force the network to learn in this fashion. And in addition to this kind of idea of learning the residual, an added benefit for extremely deep networks is that by allowing the skip connections to kind of connect to one another, one after the other, so if you have a series of these skip connections, the network can actually learn to skip large portions of the code or select how many layers are actually necessary by setting the kind of residual to 0, so that basically the original feature is just passed through multiple layers. It doesn't need those. It's already performing well. So it has this automatic complexity selection concept. How is this implemented? So again, as I mentioned, we want to add a skip connection illustrated here. So we just pass x through as the identity, and we want to form our residual feature by adding that original feature to this kind of incremental change. To implement this in TensorFlow, it's quite easy. We have our first layer, takes x, and this is the exact implementation from the original paper. So you take a convolutional layer, you apply batch normalization, and then a ReLU. And now we're going to go one more. So we're going to skip 2 layers. So it's a 2-layer shortcut to process that residual once more. And then before the final activation function is applied, we'll add that residual to the original feature x to get our new hidden feature for that layer. Okay, so quite simple. And lastly, another variation on this idea of skip connections and using previous features is that introduced by DenseNet, or densely connected convolutional networks. So the idea is that, as the paper states, it's helpful to reuse features. Things that you've learned in the past or earlier on in the model are likely to help or be beneficial in the learning process later on in the model. And so what they propose is to introduce blocks of layers which are densely connected in the sense that the features produced at this first layer in the block are used as input for all subsequent layers, at least in this block. Okay, so for instance, if we have 5 layers, this will be the input for the remaining 4. These features will be passed as input to the remaining 3, etc. So we're always passing down the features that we've created, and in particular, we're concatenating those or passing them all together. The blocks that they propose to use, or the way that they propose to implement this, is by simply providing a skip connection within a kind of a 1-layer skip connection, which will be concatenated with the features produced. So this identity will be the original features, or the features from the previous layer, or the concatenated features from all previous layers further down in the block. And here we'll create kind of the new features. So we get the features x0 through x l minus 1. Those are the concatenated features from previous layers. And we want to produce the new features xl. Those will be the results from this convolutional layer. And we'll concatenate that to get the vector x0 to xl, which is passed on. To implement this, we can actually do it quite easily. We just define 2 functions. One will be the block layer, and another will define the block as a whole. So in particular, we can define a block layer by applying this batch normalization, the rectified linear unit, again following this formulation here, along with the convolutional layer, and then concatenating that with the original inputs x, just as illustrated in that diagram. And so to create a block with, say, k layers, we just repeat this by saying x is the block layer produced by x with the specified number of channels, and that x will be grown as this loop is executed. And I should mention that Just as a final word, there is some kind of difference between this and the layers that we've seen before. So we have this batch normalization and the activation function before the actual convolution layer. This is referred to as pre-activation, and you can read more about it in this paper by He Zhang, Ren, and Sun, which goes over some of the different possibilities for skip connections and different uses of identity mappings within networks. So that's all I have for today. Tomorrow we'll go over some actual kind of deep models, such as generative models and autoencoders, and go over some of the more specific implementation details and go through some code in a more workshop-like fashion. So just let me know if you have any questions. I'll stick around after if you want to discuss one-on-one. And thanks again for coming out today.